Hello and welcome to the third lesson in this unit. Today our topic is Pascal's principle, and your learning goal. I want you to be able to state and explain what is Pascal's principle in terms of the transmission of force in an enclosed system, a liquid system. So we're looking at pneumatics specifically today. So the note in front of you has Pascal's principle, the definition, or what is Pascal's principle, and it simply says that pressure applied to an enclosed liquid is transmitted equally to every part in the liquid and to the walls of the container. So that means that basically what this boils down to is pressure is uniform throughout. So if it is under 20 psi or 20 kilopascals, it's 20 kilopascals everywhere. All right, so down here in this diagram, we're looking at a hydraulic hoist. So don't write this on yours, but if it's 20 psi here, it's 20 here, it's 20 here. So everywhere within this system, if we put 20 psi on the liquid, it's 20 everywhere throughout the system. So let's talk about the hoist. The hydraulic hoist looks roughly like this, not exact, but basically what happens here is that we have a small piston over here, and that's where the small downward force, force is applied. All right, so this is the cylinder that actually does the lifting. So it's applied on the piston here. All right, so by applying that, or pushing that piston downward, what it does is it increases the pressure in the system. Increases pressure in the system. And what happens is, because it's a narrow tube, we might move the piston from let's say x1 down to a new location at x2. So that piston might be pushed down that distance there. What happens then is the pressure is then translated. All right, so the pressure enters the whole system. And because of that increase in pressure, because this large piston over here is allowed to move, so we also have a piston over here. We'll go a large piston. So this is where the car is sitting on. All right, so your car is sitting on this part of the hydraulic jack. So that large piston will raise the car. So that increased pressure is pushing up on that large piston. But the difference here is, if this is where the piston ends, so I'm going to go with x4, that's its final altitude or height, it probably started in, or not probably, it's going to be a much different length, because if you look at it, there's a volume difference here. Okay, so over here I'll just put there's a volume difference in the two pistons. All right, so there is a volume difference here, and when it boils down, or when you do the math, and I'm not going to go through and show the proof here, but what actually happens is that from the previous lesson we talked about pressure is force divided by area. So it turns out that the volume is not even a contributing factor here, because area is, and again, you don't have to remember this, but volume is your area multiplied by your height. All right, so it's that area factor that's most important for us. So the actual relationship that comes out of this result here is it's the force of the small piston divided by the area of the small piston. That ratio is equal to the force of the large piston divided by the area of the large piston. And there's Pascal's principle for us. That pressure is the same throughout, and when you are looking at two different sized pistons, that is the relationship, or how the forces translate, and it's the area of the piston which plays the large role here. So this area versus this area. Okay? So that is the relationship. That is the formula you want added to your cheat sheet. Force, S for small, L for large. And I got a couple of examples to run through with you. So a 1,500 kilogram car is hoisted in the shop with a large cylinder press. So let's keep the diagram simple. Here's the system, and here's the car. Oops, I can't write the word car apparently. Let's try that again. CAR. Okay. So 1,500 kilogram car, we need the force. Okay. So the force of the load, or the large piston, to move that car is going to be from unit 2, mass times gravity. So 1,500 times 9.81 gives us 14,715 newtons. So that is the force being sitting on that large piston. Okay, area of the large piston. So area of the large piston is about 2.5 or 0.25 meters squared. So that's a 28 centimeter diameter. So for people that are trying to visualize this, 28 centimeters, it's almost a foot diameter. And that's about par for those types of lifts. Now the small piston, this is the little cylinder that your hydraulic pump is running. The area of the small cylinder is 0.02 meters squared. And that's about 8 centimeter diameter. So those numbers that are in the brackets here are simply just to give you a visual on how big are we talking here. So an 8 centimeter diameter, all right, you can wrap your two hands around that cylinder, maybe even smaller than that. So A part, answering that question, determine the magnitude of force of the small piston needed to raise the car. So we want to know how much force do we have to put into the system to lift our car. So we have all the information. We have three values. We know the area of the small piston. We know the force required on the large piston. And we know the area of that large piston. So now it's just a matter of calculations. Again, just reviewing math skills. 0.02 is dividing there, so the opposite of dividing is multiplying. When you do those calculations, 14,715 times the 0.02 divided by 0.25 tells us that we need to apply 1,177.2 newtons. All right. Now, if you make that comparison, if you look at the car, look at how much less force is required here. There's my magic pen here. So if you look, you need 12, so let's say 1,200 newtons to lift a 14,000 newton car. I mean, you're looking at a factor of 10. It's 10 times easier to do it with this particular system. So that's quite a huge difference with this particular press. And determine the pressure in kilopascals inside this hydraulic press. All right, so B part. Well, we know pressure is calculated with force times area. And what I'm going to do for this particular question, I'm going to do the two different forces. So if we do the small piston, 1,177.2 divided by the area, we get the amount of pressure on the fluid. So this is the pressure that's on the oil inside the system. We find it to be 58,860 pascals, which is 58.86 kilopascals. All right, and just to emphasize the point, so this is pressure on the small cylinder. What happens if we would have done the calculations for the large piston or the large cylinder? And probably you're sitting there saying, well, I already know what the answer is going to be, but I'll let him think he's going to show me something fancy here by letting him do the calculation. And 14,715 divided by, this also comes out to be 58,860 pascals, which is that 58.86 kilopascals. So exact same. So you can't mess this up. Well, what piston do I pick? It doesn't matter. All right. So therefore, it is 58.86 kilopascals. All right. And remember, the reason for this is because I said, get my pen de magique, Okay, so it's 58, oops, not there, 58 pascals here. Can't make an 8 with it. 58 here, 58 here. The pressure's the same anywhere you go within that system. So that's why it doesn't matter which piston you pick. Okay, so there you go. Simple example showing how to do the pressure calculations and force calculation. All right, and finally, I want to talk about brake technology for a second. And I know this is probably simple. It's a simplified version. For those that are a little bit more into the automotive, you're going to know a little bit more than what I'm going to express here. But I want to point out a couple things here. First of all, you'll notice that when you look at a brake system, you've got your fulcrum right here, and you have your, we'll call it the applied force here, which means that right there you have your load force. So we have a second class lever here. So we have a second class lever. And I guess I should put, this is not, well, you know it as effort force, not applied force, but the same. So when you press your foot down on the pedal, what you're doing is you are applying force to the piston. Now, you'll notice that instead of, it's the opposite of the hydraulic lift, because over here we have a large cylinder, and on the actual system, if you follow the hose all the way through, we have small cylinders. So why is that? Why is it the reverse? Well, the major reason is that this piston, when you are applying your brake, I'm going to call that distance there, that small distance, let's call it D1. Over here, when the piston's actually applied to the disc brakes, you're going to have, you know, a D2. What we want to do on the brake pedal is we want to have as less of stroke as possible. So we want D1 to be small. Why is that? Well, if you think about yourself in the car when you're driving, you don't want to have to move your leg. You don't want this distance here to move your leg. Pick a better color here that I haven't used. If this distance is like 2 feet, all right, you're going to be pumping. It's going to be like biking trying to brake here. If we can decrease that distance, if we can make this distance that we need to pump it very small, it's a lot more convenient, better reaction time, and so on and so forth. So we want D1 to be small. We want that piston to be small. So how do you make a small motion result in a larger motion at the end of it? Well, we go from a large cylinder and transfer from the large cylinder right here to that small cylinder. So what that allows you to do is to apply the appropriate pressure with a small stroke rather than needing a large one. Okay? That pressure then is passed through the system, and you can apply a large pressure then on your disc brakes. So large pressure can be applied with a small stroke. All right, so just using, it's kind of the reverse concept to the hydraulic lift on the previous page. All right, so these tubes, they run to your 4 tires. And the other reason, I'll put down here then, also, this cylinder, this piston that you're pushing, you're not dealing with one tire. You need to provide pressure to all 4 tires. All 4 tires. All right. So that means that pressure needs to be fairly big at the initial point because it's going to get spread into 4, divided by 4, when it spreads out throughout the system. All right. There's a couple of real-world examples, the hydraulic press and the brake system. You got an example on how to do the calculations. Any problems, you know where to find me. Good luck, and we'll talk to you later.